Stone, and this is my Physics 2211 Lab 5. So for this experiment, we were given the freedom to examine any system we were interested in, whether it involves an experiment or it's solely computational. And for this one, I went with the Slinky Drop experiment, of which there was a video of, and I created a script model along with the tracker analysis of the video and compared them to see how the Y position of the bottom of the spring changed over time after dropping it. So a couple essential concepts to know. First one is Newton's second law, which states that the force acting on the system is equal to the system's mass multiplied by its acceleration. And then the position and velocity update formulas, which given things such as time, average velocity, initial position, can find the final position and velocity of a system. Some more essential concepts include the force of gravity, which is equal to an object's mass times the acceleration due to gravity, which on Earth is 9.81 meters per second squared. And then also the law of universal gravitation, which, as seen there, can be rearranged to give the gravitational constant lowercase g, as opposed to the universal gravitational constant uppercase g. So if we examine the system, as soon as the slinky is let go and it begins contracting, the initial free body diagram shows that the force of tension as the spring compresses and the force of gravity are equal, which is expressed in the bottom of the spring not moving. But when the top meets the bottom and there is no more tension in the spring, the only force initially is the force of gravity and causing it to fall. And as it falls and speeds up, the force of drag begins to act on it. However, it's nowhere near the strength of gravity. So there is a net downward acceleration. Here's the slinky drop video. As you can see, he drops it and the top rushes down to meet the bottom before the entire thing falls to the ground. And here I took a screenshot of my tracker analysis. Time ranged to about 0.4 seconds. The initial position was basically 0, 0, as I set the origin, the coordinate plane at the bottom of the slinky, and the initial velocity was 0, as it was dropped from rest. Here you can see the initial conditions I set in my code, including the mass of the slinky, which is negligible, to do the acceleration of gravity being constant for all things regardless of mass. You can see my delta t time step, force of gravity, and drag constant. This was the first loop I used for prior to the top of the slinky meeting the bottom. So as you can see there, force of gravity and force of tension are equal, so there's no net movement. But in the second loop, after the moment the two parts of the slinky meet, I have force of gravity and force of drag, with force of drag being significantly smaller in magnitude than gravity, resulting in a net downward movement. This is the result of my lab. The blue line representing the tracker analysis and the red line representing the glow script code. As you can see, they both start and end the same, but the slope downward is slightly different, mainly due to some frames per second errors and mass placement errors in tracker. And that's reiterated here. Models are relatively similar. Drag didn't appear to be a significant factor, but there definitely were sources of error in terms of motion blur. I had to account for the frames per second of a slowed down video. I had to place the centers of mass by hand, which definitely did not improve the accuracy, and then just overall timing of the lab. But they began and end relatively similarly, and so show a similar pattern. So although this problem appears foreign and odd, it still relies on the same basic physics principles. The slinky dropped top first because of the tension in the slinky, which kept the bottom suspended. And if you have a mass that's like a very long rod, for example, and you hold it upright, the gravitational potential energy is measured from the bottom of it, not the middle, not the top from the bottom, which is why the bottom remains stationary and the top comes to meet it, because the bottom defines gravitational potential energy. So that's converted to kinetic energy, and the rest of the kinetic energy it gains from the top is due to the tension in the slinky, not due to gravity, which explains why the top comes to meet the bottom and it hangs suspended for a moment before actually hitting the ground.